People used to be so stupid. They used to think that the sun goes around the earth. But it turns out, see the pun there, but it turns out that that's not a stupid thing to think at all. And if you were to meet an ancient person or a modern person who thought that the earth stood still, what proof would you offer to show them that they are wrong? Think about that. Or maybe we could just say that the two orbit one another, like this dog. Is this dog following after his tail, or is the tail following after the dog? Think about that, because it's all a matter of perspective, right? Wrong. These are two totally different theories that see the universe in totally different ways. But let's start where they agree. Everyone, even those so-called ignorant ancient people, knew that the stars rise in the east and set in the west each day. That's the observation. And here we're going to be very careful to separate observations, facts, things we can agree on, to keep the observations separate from the theories or the explanations or the models or the paradigms, to use a fancy word. Again, we all agree that stars rise in the east and set in the west. But what is, quote, really going on? Is the entire heavenly sphere moving around us, or is the earth spinning? Both explanations are terrible. Think about how fast that huge, distant heavenly sphere must be moving in order to circle the Earth every 24 hours. It's much faster than the speed of light. But if the Earth is spinning, why doesn't it fly apart? And also, the Earth's circumference is 25,000 miles. So, are you saying that the equator is moving at over 1,000 miles per hour? If it is, how can the birds keep up with it? Well, if you can't answer those questions, you are not allowed to call ancient astronomers stupid. Again, we all agree stars rise in the east, set in the west. So does the sun and the moon. They are stuck on the starry background. But over the course of the year, the sun moves from right to left through the constellation. Constellation to constellation, names you'd recognize: Aries, Taurus, Gemini, Cancer, etc. This motion takes the sun to greater and smaller declinations. That's the seasons. We are not talking about the seasons. The moon completes the same right to left path through the constellations every month. We are not talking about the phases of the moon. Again, everybody agrees on these observed facts. And if you're thinking to yourself, gee, I've never seen stars behind the sun. Of course not. They're washed out in the daytime. But you hopefully you've noticed seasonal changes in nighttime constellations. If not, go outside and look at constellations more, and in the meantime, take my word for it. Here is a geocentric explanation for the yearly motion of the sun. The outer sphere moves just a bit faster than the sphere of the sun. If the sun goes around 360 degrees in 24 hours, the stars move about 1 degree further. Those minor differences add up, and the stars, quote, lap the sun every year. So it works. The heliocentric explanation is very different. The motion of the Earth around the sun causes the sun to seem to move from background constellation to background constellation throughout the year. Again, we are trying to distinguish between, we are not just trying, we are distinguishing between observations and explanations, and this gets sticky. We talk about the sun, quote, moving from Aries to Taurus. That's the observation. And then we say that the sun is, quote, stationary. That's the explanation. So does the sun move in this model? Well, yes and no, depending on what you're talking about. So you have to be clear. It's difficult. So these theories are very different, even if the observations they explain are the same. But the motion of the sun is simple and straightforward compared to the planets. Planet is the Greek word for wanderer. Planets are wandering stars. They go from constellation to constellation, but their motion is complicated because they reverse direction and move from left to right. They go retrograde, which is crazy. How are you going to explain that? Here are some photos of Mars. Each one was taken about 2 weeks apart. Mars starts in the lower right and moves to the upper left with a major zigzag. And it takes months. It can take months for Mars to finish going retrograde. And it's only swinging backwards about the same angle as if you were to hold your hand out at arm's length. That's about the angle that Mars is moving backwards in the sky. So this is definitely not something you would observe if you were looking at Mars just one night. All you'd see Mars doing is, like everything else, rising in the east, setting in the west. So that's Mars. Two main questions now. Mars gets brighter when it goes retrograde. Why? Also, Mars only does this retrograde motion thing when it is in opposition, when it is opposite to the sun in the sky, when it rises at sunset and is highest above the horizon at midnight. Why? We now have a major challenge for our theory, heliocentric or geocentric. Predict with precision when and where Mars will go retrograde. Put it in writing, take the risk, and if the observations match your predictions, I will believe you. And what I said about Mars holds true also for Jupiter and Saturn, but not for Venus and Mercury. They also go retrograde, but with a very different effect. They stay close to the Sun. Not close as measured with a tape measure. Close as measured with a protractor. Close in angle. They stay in neighboring constellations to the Sun. Sometimes to the right, morning stars. Sometimes to the left, evening star. Explain that. Okay, I will. Here's the planet going around the Earth, being pushed in its orbit and also swinging around on an epicycle. A sphere moving on a sphere. This arrangement makes all sorts of different shapes, and it can be used to make the planet, quote, swing backwards against the background stars. Notice how the planet gets closer to the Earth? Haha, the brightness question is answered. And this might seem weird to you if you're used to heliocentric orbits, but notice how well the theory, planet swinging backwards in space, matches up with the observation, planet swinging backwards against the background stars. Great, but not perfect. Something is missing. The link between going retrograde and the position of the Sun. Why is that? More on that later. First, here's Venus. How can you get Venus to always stay near the Sun? Easy. The deferent of Venus moves at the same speed as the orbit of the Sun. Then the epicycle of Venus takes it to the right or to the left of the Sun, and we're done. Geocentrism has saved the phenomenon. It has explained why planets go retrograde, why they get brighter, and how they can stay near the Sun. But science is never done. It's a good theory, but it's not great. It explains the observations somewhat, but it was never able to predict with precision, exactly, down to the minute, when and where the planets would be, when they would go retrograde. And another problem, it does not explain itself very well. Specifically, why is the epicycle of Mars linked to the deferent of Venus? That is so random. Also, I count 5 moving spheres for just 2 planets. Can't we, tidy this up a bit? And I should note that this is a very simplified version of the theory. In order to improve their predictions, astronomers added more and more and more epicycles and other complexities. But still, can't we tidy this up? And before we see the heliocentric view, let's review the observations one more time. Planets change direction, they change brightness, and 2 stay near the Sun. We can explain this in a brand new way. Let us combine these spheres. They moved at the same speed anyway, so let's combine them together. And there you go. A tidied up solar system. One that explains why Mercury and Venus stay near the Sun in a new way. Notice that the observation, close to the Sun in angle, now harmonizes with the explanation, close to the Sun in distance. A more elegant model. No more insisting on cycles moving at the same speed. And what about Mars? Again, this new model is more elegant. Both Mars and Earth orbit the Sun, but the Earth moves just a little bit faster and flies past Mars in the orbit. No longer is there a need to make Mars turn around in order to go retrograde. 2 more things. Number 1, this again explains brightness with closeness, if you look carefully. And number 2, and more importantly, this model gives a good, physical, non-arbitrary reason for why Mars can only go retrograde when in opposition to the Sun, when the Earth is flying past Mars in the orbit. What was random and arbitrary in the old system is now necessary in this new system. And to review, the heliocentric system is simpler than the geocentric model. If you try to draw out all those orbits and epicycles, you'll find that they crash into one another, which is bad. So progress. But there is a price to pay. This new model of, quote, what's really happening is divorced from our observations. First of all, the Earth is a planet. It's a wandering star. That's weird. Venus is this glowing dot. It's romantic in the evening or in the morning. But the Earth is not a glowing dot in space. I guess it would be if you were living on Venus, but we're not. The Earth is muddy. And I know what you're thinking, though. It doesn't matter. Elegant or muddy. It doesn't matter. Just tell me which one is right. Okay, fine. The answer? Neither of them. At least not this heliocentrism, the one presented by Copernicus in the 1500s. His main problem? Insisting, like everyone else before Kepler, insisting on perfect circular orbits. But asking, quote, who's right, that's not the right question to ask. The real question is who's going to win when you put them side by side and put them into a death match? Which model will be able to predict when and where Mars goes retrograde? And the winner, obviously, is neither of them. It's a tie. Neither model is great. At least heliocentrism before Kepler and Newton, not great. So, is this just a case again of the dog chasing his tail? One model just being as good as the other? Some people like heliocentrism, some people like geocentrism. We can all just, call the whole thing off? Not at all. Because there is a third thing that our scientific models must do. We've talked about making predictions. We've talked about being internally consistent or elegant. But there's a third thing. Good models must be able to calculate stuff. And this is where Copernicus is the clear winner. Using trigonometry that he inherited from the Arab world, Copernicus was able to calculate the relative distances from the Sun to the inner planets. Venus's angle of greatest elongation, its maximum angular distance from the Sun. That's all you need in order to chart out its orbital distance from the Sun with a little geometry. So which model will win out in the end? Obviously, the one that's more fun to use, the one that allows scientists to calculate stuff. That's what they like doing. They can also find the orbital distances, the relative orbital distances to the outer planets. This takes a little bit more work, one more step, but it's pretty much the same thing. And we'd have to wait a little while until the late 1700s in order to get absolute values in miles or kilometers. But still, the geocentric view had no way at all of determining these values. But the heliocentric model doesn't stop there. If you plot out the orbits, you can find orbital velocities and relationships like Kepler's third law. So if you ask a scientist which model he or she likes better, it's always the one that lets them draw graphs. Scientists love graphs. And I'm not saying that there's no proof of heliocentrism, but what do you mean by proof? Are you looking for an observation, a clear-cut observation that can be explained with heliocentrism and not with geocentrism? Well, if you are, then maybe you'll accept the phases of Venus as your proof of heliocentrism. But it's really not that simple. These same observed phases, thank you Galileo for the telescope and everything like that, for using the telescope to look at these phases. These phases, though, could be explained with another theory. They could be explained by Tycho Brahe's weird theory. Brahe had the planets revolve around the Sun, and then the Sun orbit a stationary Earth. His compromise theory, a classic compromise, one that makes nobody happy. Also, whatever proof you come up with for heliocentrism, there's still one big question. Whose heliocentrism? Are you talking about Copernicus's model with circular orbits? That's wrong. Even Newton's theory. Newton, who was so successful for Neptune and for comets, Newton's theory was incomplete. It was wrong. You could call Newton wrong. His theory was wrong when it came to Mercury. He needed some backup. He needed some backup from Einstein on that one. The interplay between theory and observation is complex. That's the point here. It's not just a matter of being right or being wrong. It's not just a matter of being smart or being dumb. So don't call ancient astronomers dumb. After all, there is a very, very good reason for not believing in heliocentrism. The complete lack of observed stellar parallax. If the Earth is moving around the Sun, if that's real, we should be able to get a new perspective on the stars from season to season. Just like the world looks slightly different from your left eye than from your right eye, which are really just a couple centimeters apart, we should see a difference in the stars, but no stellar parallax was found. Aristotle considered the heliocentric model, but he rejected it for just this reason. Even if there is no, quote, nearby star to look at least the North Star should change its position throughout the year. It should trace out a small circle if the Earth really is moving, but it doesn't. Astronomers kept looking and looking for a stellar parallax, but never found any. No final nail in the coffin of geocentrism. Even after they had figured out using parallax again the distance from the Earth to the Sun, they did not see this stellar parallax. They never found it, but never is a long time in science, and you can't ever say never, because finally in the 1830s, stellar parallax was observed by this guy, a small motion, a couple millionths of a degree. So that was success, and today observed stellar parallax is our tool for finding distances to nearby stars, but that's not the point. The point is that all the geocentrists were gone way before the 1830s. Why? Not because they were, quote, proved wrong, but because of the things we were talking about already. What makes a good model? What makes heliocentrism a good model? Number 1, matching up with predictions with the help of Newton, check. Number 2, having internal coherence or elegance. All those harmonizing spheres, check. Number 3, allowing scientists to calculate stuff and draw graphs. Double check.